User preference and the example of basic probability. Suppose there are two classes, positives and negatives, black and green, although we're going to use gray in place of black. Gray fast food versus healthy greens, or business gray versus stylish green. We don't always use our preferences. For example, if we're with a downtown lunch crowd, we may prefer healthy, but sometimes fast is necessary. To illustrate this, we're going to look at a simulation called My Favorite Die. This is a random experiment. We're going to do 1,000 trials. Capital X buys the outcome of the ith trial. And we're going to have a favorite die, a user preference. We randomly choose either a 6-sided or 8-sided die. The 6-sided is green and the 8-sided is the gray. We're going to choose one at least twice as often as the other. In other words, we're going to have a favorite. The one we choose most often is our favorite, our preference. And we'll roll the chosen die and record the result. The green die will be numbers 1 through 6. Notice that the gray die is 0 through 7. So let's suppose you like the green one. So you roll the die and it comes up as a 5. You roll again. You've randomly chosen the green and it comes up as a 2. Now you randomly choose the gray, and you roll it, and it comes up a 5. And so on and so forth. And if observation 1, we're going to say, is of someone who uses the 6-sided green die twice as often as the 8-sided gray die. So most of their entries come from the green. So in each of the 1,000 trials, she rolls one or the other, but she favors the green one and uses it twice as often. Now let's suppose observation 2 is somebody that likes the gray. That means most of their entries are going to be gray and not green. There's two distinct classes here. Class 0 who prefer the green and class 1 who prefer the gray. Now remember, each trial, each random choice of a die and subsequent roll is independent of every other trial in the experiment. So let's suppose we have some data. So in observation 2, do they have a preference for the 6-sided or the 8-sided die? In observation 14, do they prefer the 6 or the 8-sided die? The answer comes from the fact that we have two random processes with variables x associated with the 6-sided die and y associated with the 8-sided die. And we have two classes of behaviors. Class 0 prefers the green, x twice as often as y. Class 1 prefers the gray, y twice as often as x, at least. We actually have two random variables, x and y. Let's look at the averages. So we have numerical outcomes, x1 to xm, and we're writing our outcome space as x1 to xm, so these are actual numbers. So in the Favorite Die case, the S is 1 through 6. And so the average is just the sum of x times the probabilities, where x is all the possible outcomes in S. For the 6-sided die, we're adding j equals 1 to 6, x sub j, p of x sub j. All the p of x sub j's are a 6, so we get 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6, 6 added together. That's 3.5. The 8-sided die, the probability of all these is 1/8. Notice that our variable here is the capital Y. And we do the same thing, and the mean here is also 3.5. That's why we chose it to go from 0 to 7, by the way. So the two die have the same mean. But that means the spread, or the variance, is where we're going to get the answer. So the variance of x, if mu is the mean of a variable x, then the variance is the expected value of the difference of x minus mu quantity squared. For the 6-sided die, the variance looks like this. Everything subtracting the mean, and we get 2.9166. The same calculation for y gives us 5.25. Now if n is large, we can approximate this theoretical calculations of variance with variance over the sample population. So the variance will be what's different. So variance of x is going to be less than variance of y. In other words, y is more spread out than x because we use the 8-sided die more often when we're in the y. So the variance for class 0 is less than the variance for class 1. We use x twice as often as y, then we get the variance of class 1 as an upper bound of 3.69. Now this is theoretically. In practice, it won't be exactly that upper bound. And for class 1, we get y twice as often as x. So a third the variance of x was 2/3 the variance of y, and that's 4.47 theoretically. But that gives us a way of measuring when we're in class 1. So in the observations, in observation 2, they like the green. The variance of class 0 is less than 3.69. And if they like the gray, the variance of class 1, which is greater than or equal to 4.47. 3.688 in observation 2, so their favorite die was the green die. In observation 14, variance is 4.496, so their favorite was the 8-sided. And it gets better. The law of large numbers says that empirical, which means from the data, averages approach theoretical expectations. It's the number of independent trials that approaches infinity. So for very large n, we'll begin to get exactly these kind of variances, 3.69444. Similarly for class 1. The bigger the data, the better the results. This is true in general when you have purely random. The more data, the more confidence you have. But we have a problem. This isn't really a good model of user preference. People don't randomly choose while tracking if their favorite is used twice as often. General preferences are probably different in every different situation. But let's go back to the lunch example. Where do you go to lunch? Well, you get with a group of coworkers, and the group of you decide where to go. There's still randomness, but there's not enough independence for you to be able to use the law of large numbers to estimate expectations. So let's suppose we have the downtown lunch crowd. 1,000 workers each play the My Favorite Die 1,000 times. Half are gray and half are green. And so for the original version of the game, you can see the separation there. Very easy to classify them into either class 0 or class 1. But now let's suppose they play this game. So they form into groups of 1 to 5. Each member of the group votes their preference. The most votes determines which of the 2 die to roll, the gray or the green, and the result is the same for the entire group. So this is what the variance looks like in that case. Can't really determine necessarily who's gray and who's green like you could with the original. I did the same thing for a 4,039 node Facebook network, and this is what it looks like. There is some definite separation, but again, there's a lot of overlap. Variance alone doesn't predict preference. So we've got to use the underlying structure, this forming into groups. So the point is the complexity has a structure. The trials are still independent. The expected values are still the limiting values of the sample averages. But the theoretical is dependent on a complex and often unknown underlying structure. So the theoretical is not nearly as easy to write down as it would be if we had a purely random process. We can use the structure, however. So for instance, we do know that green is twice as often as gray if the variance is low enough, and the gray is twice as often as green if the variance is high enough. What about those in the middle? Well, Well, the first time through, we can use variance to identify the two groups, and then the next time through, we can use nearest neighbors after pre-processing to help identify which people went to lunch together. And that means we can use the nearest neighbors classifier. So in summary, statistical models assume simple models of individual actions, allow accessible theoretical models because everybody's acting independently and identically. But for us, in the big data world, you can't ignore the underlying structure. There are social networks, such as those groups going to lunch, and there is dependence among individuals. And preventing assumptions of uniformity and simplicity means that we do need all that big data in order to make the kind of predictions we want to be able to make.